So it's my pleasure to introduce Holger Mueller, our AMO speaker for this week. So reading up on Holger on the internet, I discovered that he successfully applied for his first patent when he was 14 years old. He was an undergraduate at the University of Constance and received his PhD from Humboldt University in Berlin, working with Achim Peters. He was an Alexander von Humboldt Foundation Fellow with Steve Chu at Stanford and has been faculty at Berkeley since 2008. He's a precision measurement wizard, and I'm really looking forward to the science he has to share with us today. So,
all right, Holger. Thanks so much for giving me the opportunity to speak here, and thanks for listening. So this is mostly about the fine structure constant measurement that we did with Atom-interferometry. You can see that see now the laser pointer isn't working anymore. I'll use the mouse pointer. I hope this is visible. So there, the fine structure, here's a bottle of Texas bourbon whiskey we gave the postdoc when he finished the project. And it's 137 proof, okay, like the fine structure constant. These are the most accurate measurements of the fine structure constant, and we'll go over this in detail. But first, why bother? And the reason why we bother is that the standard model is incomplete. We know exactly what we don't know. There are loud and clear signals from the skies that point to the existence of dark matter and dark energy that make up almost the entire mass energy content of the universe. Regular matter is only about 4% of it, and only 0.4% of the total mass energy is things like stars and planets. So our standard model of physics describes these 4% successfully, but we know very little about dark matter. We know essentially what it is not, and we know even less about dark energy. And yet, all our attempts to find signals for dark matter, let alone dark energy, in detectors on the ground, have so far not yielded an uncontroverted discovery. Here's the discovery of dark energy. If you were an astronomer, an astrophysicist in the early 90s, you might have measured the observed magnitude, that is brightness, of supernova relative to the redshift. The redshift of a supernova is a measure of how fast the supernova recedes from the Earth, which is a measure of how fast the cosmos expands. And the magnitude of the supernova is a measure of how far away it is. So these curves here are relationships between distance and speed in the history of the universe. And in the early 90s, all was known about these curves was the part from a redshift of 0 to 0.1. Okay, and all of these points lie on the diagonal curve, which means the universe is expanding at a constant rate. Now, obviously, gravity should make the universe contract. That means the initial expansion would slow down, and the big question was, would it eventually stop and turn around, or would it keep going forever, never really slowing down enough to stop? To the big surprise of the involved researchers, it turns out that when they had more data out at higher redshifts, all those points accumulated above the diagonal line, giving evidence for an expansion of the universe that accelerates, contrary to what everybody expected from gravity. I'm showing this graph to make one point. Sometimes when you can measure something an order of magnitude further, redshift of 1 versus 0.1, you can make an important discovery. In atomic physics, we're measuring further all the time. So this slide shows the accuracy of atomic clocks from 10 to minus 10 for the first cesium atomic clock by Essen and Perry in 1956, to the most recent atomic clocks as they are built, for example, in Boulder, Colorado. And the very latest ones are not even on this slide. They would actually be below the 10 to the minus 18 level. Now, if you draw a line from the first clock to the most recent clock on this graph, you will find that the precision doubles every other year or so, which means we're gaining an order of magnitude in accuracy faster than once per decade, okay? This is comparable to the growth rate of COVID-19. Well, not quite. COVID-19 is better. But the hope is, of course, that if, let's say, dark matter has an influence on the ticking of clocks somewhere between the 10 to minus 18 region shown here, you can extrapolate the progress and estimate that in a decade or two, we will be able to see it. Okay. Now, I'm not involved with any atomic clock development that allows me to brag about the previous slide. Let's come to interferometry, the particular technique that we're going to use. Everybody knows the LIGO signals for the discovery of gravitational waves. What LIGO essentially does is it takes a laser beam, splits it into two interferometer arms, and after they have traversed an enormous distance of hundreds of kilometers, right? The arm length is 4 kilometers, but cavities in the arms mean that each arm is traversed hundreds of times. So you have a travel distance of hundreds of kilometers and a wavelength of light of 1 micron, and the ratio between those scales gives you a huge enhancement factor of a tiny signal, because it means a part per trillion change in the arm length makes a difference of 100% in the detected intensity of radiation. Okay, so that's for light interferometry. And remember, the fact that we can make the arms much longer than the wavelength gives us a huge lever arm for increasing the sensitivity to tiny signals. We can do the same with matter waves. Here, this is Louis de Broglie in 1924, who has just discovered this relationship between the wavelength and momentum of matter waves, right? You would have a source of matter waves, just like a light interferometer needs a source of photons. There's actually an important difference here. Virtually all precision measurements with light are now done with lasers, even though you don't have to. You could run an interferometer with white light. If the arm length is equal, then you have built, a so-called white light interferometer. If the arm length is equal, then even light of short coherence length will produce an interference pattern, right? With atoms, this white light interferometer is the usual case, and not every atom interferometer starts with the analog of a laser. It doesn't start with a BEC necessarily. There are complicated reasons why and why not. Historically, of course, BECs were not always available, but even nowadays, the higher thermal energy of atoms in a non-condensed sample has advantages, actually. We will see that one of the most important systematic effects in our measurement of the fine structure constant is our ignorance of the details of the wavefronts. In other words, real laser beams always have a speckle pattern, and a thermal atom with its thermal velocity orbits inside the laser beam and averages over the speckle pattern, reducing systematic effects. We didn't know that when we designed the experiment. We didn't know that speckle would be a limiting influence, but we were happy to learn that this was the right decision. Anyway, the atoms are treated as waves. They undergo beam splitting. They fly on two paths. We will talk about how the beam splitter works. Mirrors, also made of laser beams, will put the partial wave packets together. And then constructive or destructive interference in a detector will tell us about the phase difference between the two arms. As already said, de Broglie hypothesized matter waves, and 4 years later, Davison and Germer showed the first evidence for electron interference in 1928. In the early 90s, the field really took off with simultaneous developments in 3 groups. Carnell and Blueneck in 1991 built an atom interferometer with material gratings as beam splitters. Then there was Kasevich and Chu with the light pulse beam splitter, and also Fritz Riele during about the same time. The technology that is most useful for precision measurement is the light pulse atom interferometer, because here the diffraction happens at standing waves of light, whose wavelengths are very well known if you know the laser frequency. So you have a tool here to leverage the high precision of laser wavelength measurement for your interferometer. So to recap, light pulse atom interferometers, particles are waves. How do I calculate the phase difference between those two paths? Well, all I need to know is the Lagrangian. If I know the classical Lagrangian of the particle, that includes gravitational potential, kinetic energy, perhaps other potentials acting on the atom, then I can calculate the classical trajectories of the atom through the interferometer. And the line integral across this closed loop enclosed in the interferometer arms gives me a first contribution to the measurable phase difference. The action on the upper path minus the action on the lower path is divided by h bar is the so-called free evolution phase. Secondly, whenever the atom interacts with a photon, the photon's local phase gets added to the phase of the atomic wave function. That contributes a phase shift whenever the atom interacts with the laser. And so this can all be calculated with standard methods. Let me drive home what I already said, namely the lever arm provided by the fact that the matter waves makes many cycles on each interferometer arm. Here's a mathematically generated plot of the measured atom number as function of phase, and this plot is to scale, but we don't see anything because the finesse of the fringes is so high. So we zoom in several times until we see data, and this is real data that I can brag shamelessly about because I haven't measured it. It's been taken by Kengyao Chang in the 90s. So this data is not even state-of-the-art data. And of course, the entire community hopes that they can improve things in the future. All right, let me give you but 3 examples out of a very large number of potential atom interferometry applications. The first on the left-hand side of the slide is the measurement of Newton's gravitational constant, was first done by Kasevich at Stanford. And the latest one is by Joe Mutino in Florence, who measured Newton's constant to an accuracy that is almost comparable to the accuracy obtained by torsion balances, but using completely different tool. So this is a good check. You know that the systematics of Newton's constants are a thorny issue. So a measurement which uses a very different method is of particular value. The central one is what I'll focus on in this talk. And on the right-hand side, you see a stunning result in which the Kasevich group has split a matter wave packet by as much as 0.5 meter, put it together and recorded interferences. And these measurements are powerful tools to test general relativity and perhaps one day even look for gravitational waves. All right, here is the fine structure constant. It measures the strength of the electromagnetic interaction. Let me actually hold on at this point to give you a chance to ask questions.
Okay, so I think actually Dan has a question, and maybe I'll let you ask that yourself, Dan, unless you want me to ask it for you.
Why don't you go ahead?
Okay, so Dan's question is, you say that atom interferometers face a systematic error from tiny variations in phase of the optical wavefront. Does something like that also happen with optical clocks? How can you compare the 2 situations between an atom interferometer and, say, a Ramsey interferometer and an optical clock?
Probably there are people on this Zoom call that know more about clocks than me, but let me just make one small remark. In theory, even if you're, let's say, fundamentalist, you could even call an atomic clock an atom interferometer because the interference happens between the atom being in the excited state and not in the excited state. But what I mean by atom interferometers in the narrow sense is a device in which the relative motion between the interferometer arms generates all your signal or most of your signal. And in a clock, there may be motion, but it's a side effect. It's not the signal you want. In an atom interferometer, motion leads to the signal. Since that motion arises from momentum kicks from photons, and if I have perfectly smooth wavefronts, then you know what the momentum of the photon is. It's just given by the laser wave number. But if the wavefronts are squiggly, then the local wave number varies, and thus your signal varies. So I would say in an atomic clock, I'm sure that such effects happen, but they are suppressed because they are not the cause for your main signal, whereas in our case, the laser beam and the momentum of photons is the cause for the signal I'm after. I'm not sure if that answers all the question.
I think it does. So Aruku Senu asks, why is coherence not destroyed when you use a thermal cloud as opposed to a coherent atom beam or BEC for atom interferometry?
Let me answer by an analogy to light. If I take light from the sun or from a light bulb, we say it's incoherent, by which we mean it has a very short coherence length, perhaps of a micron or two. That means if that white light travels by exactly the same distance on two interferometer arms within the coherence length, then I get interference fringes. The magic of the laser is that the coherence length is extremely long, and so I can build interferometers with different arm lengths. The interferometers that we're talking about in this talk are all white light interferometers in the sense that they do not suffer from the coherence length of the atom source. In fact, we can measure that if we change the relative arm length by on the order of 100 nanometers, then we see that our contrast suffers. So the coherence length of our samples is hundreds of nanometers. Is that an answer to the question?
Yeah, I think so. Thanks. So I'll ask one more and then maybe we'll move on. So
Cool.
Storm Weiner asks, a BEC wave function is distributed in space as well. How does this differ from the thermal cloud in regards to averaging over wavefront distortions?
They don't move as much. So there are two, in the context of this question, the only property of the BEC I use is that it's very cold. The the motional energy of each atom is very, very low. So the atoms move very slowly, and an atom that is stuck might be stuck at a point with an atypical local wave vector, okay? So no averaging happens because the atoms don't move so much. Yes, in a BEC, atoms are also all in the same state, but that doesn't matter so much for answering this question. It's just the temperature that matters here.
Okay, great. Why don't we move on for now and wait for the next break for more questions.
All right, the fine structure constant. Let me actually take some excursion here, and not all fundamental constants are created equal. In fact, the most famous things like the Planck constant or the speed of light, I wouldn't even call fundamental constants. Why? Knowing that the speed of light is 3 × 10⁸ meters per second in SI units doesn't tell you anything about physics, because the number is different if I measure it in whatever inches per day or furlongs per fortnight or something like that, right? And that's why theorists can get away with not knowing what C is and simply set it to 1 by appropriate choice of units. And the same is true for the Planck constant, the same is true for the Boltzmann constant. They are more unit conversion factors than numbers that tell us about nature. There are different numbers that do tell us about nature, and they are always ratios between measurable quantities. The simplest example that we learn in elementary school is the number pi, the ratio of the circumference to the diameter of a circle. Now, the number pi we have learned how to calculate with very high accuracy, so we don't need to measure it. The fine structure constant is similar to that. It has a value of 1/137 in any units because it's a ratio between measurable quantities. For example, it's the ratio between the Bohr energy of an electron in the lowest hydrogen orbital and the rest mass of the electron. So it answers the question, by which fraction does the energy of an electron go down when it binds to a proton? Likewise, it's the ratio between the scale of the fine structure and the principal energy levels, or the hyperfine structure, and so on. All these are powers of alpha. And so, vexingly, the fine structure constant, by contrast to the number pi, cannot be calculated. In the words of Feynman, there is no way we can program a computer to spit out the fine structure constant without secretly putting it in. So this is a number that the theorists need to memorize. They cannot set it to 1. And importantly, it has to be measured. It can't be calculated. Being a measure for the strength of electromagnetic interaction between elementary particles, it's not surprising that the fine structure constant is important in all of physics, and correspondingly, methods from all of physics have been used to measure alpha. For example, spectroscopy on muonium, neutron interferometry, measurements of the geomagnetic factor of the proton, the quantum Hall effect from condensed matter physics. But the most accurate measurements come from 2 methods. The first is measuring the gyromagnetic anomaly of the electron. So the electron has a magnetic moment, which is a bit more than 2 Bohr magnetons by the so-called G factor. And the difference of the G factor from 2 can be calculated using quantum electrodynamics to extreme precision. From measuring this gyromagnetic anomaly, I can use the theory of quantum electrodynamics to back out the fine structure constant. And the second measurement method is measuring the ratio of the Planck constant to the mass of an atom. Now, the international system of units has been revised recently, and the Planck constant has been given a defined number. So we could now say we're measuring the mass of atoms and not just the ratio of H over the mass of atoms. That's a semantic issue. Okay. The fine structure constant can also be predicted to be 1 over 137 from biblical sources and from the fact that the chlorophyll molecule contains 137 atoms, and of course from the fact that good whiskey is 137 proof. Okay. The fine structure constant I mentioned can be measured, and then I can use quantum electrodynamics and to predict the magnetic moment. Let me comment a little bit on how that works. Julian Schwinger calculated the famous leading order correction that I've normalized here to 1. That's the leading order quantum electrodynamics correction. At the current accuracy, this has to be calculated up to the 5th order, involving over 10,000 Feynman diagrams. These are horribly complicated calculations, and every year or 2, there's a small correction to these calculations that actually shift the value derived from G-2 by a tiny bit. At the accuracy of current experiments, not just quantum electrodynamic matters, but the existence of muon comes in, the weak interaction comes in, the existence of virtual hadrons comes in, and that's actually a thorny issue because perturbation theory doesn't work well with a strong interaction. So large parts of the standard model are employed in the calculation, and if the calculation is confirmed experimentally, that means large parts of the standard model have been tested. The key message here, however, is if the existence of the muon shifts this calculation, or of hadrons, then the existence of as yet unknown particles will also shift the calculation around. And so measuring alpha and comparing to the value of G-2 is a very broad method to look for new particles in the standard model. Other methods to do that have been used. For example, measuring electron-electric dipole moments. So let me address that a little bit. If I want to look for new physics, should I measure EDMs, should I measure alpha, or should I do both? The answer is you should do both. Here's why. The electromagnetic moment, the electromagnetic anomaly is non-zero in the standard model. And the only way I can get a limit on new physics here is by comparing a prediction for the non-zero anomaly with the measured anomaly and taking the difference. So I need to subtract 2 large numbers looking for a small signal. Okay, that's hard. On the upside, there is no symmetry that protects a new interaction from entering the calculation of G-2. With EDM measurements, on the other hand, the standard model signal is extremely small because symmetries prevent most physics from causing an EDM, right? you have to break the symmetries of the you need a symmetry violation before you have an electron-electric dipole moment, and that rules out most of the large electromagnetic interaction from contributing here. So as soon as I have measured a non-zero EDM, I have a signal for physics beyond the standard model. On the other hand, if the signal preserves CP and T symmetry, then I won't measure it in an EDM measurement, but I can still measure it by comparing the fine structure constant with the magnetic moment. So I would say comparing alpha with the magnetic moment is a broad search for new physics, whereas EDM measurements are more targeted search for new physics. Good. One example is the muon G-2 measurement. The magnetic dipole moment of the muon is known to deviate from the standard model prediction by I forgot the number of sigmas. It's shown here. Something like 3.6, 3.7 sigmas has been argued to be the strongest evidence for physics beyond the standard model. It has been ascribed to a so-called dark photon, also called massive photon, and there have been massive efforts to look for dark photons. Let me show you one. These are some limits on dark photons. Here's the dark photon mass from an MeV to 10 GeV. Here's the dark photon mixing angle. That's something like a coupling constant. And the colored regions are the ones that have been ruled out, for example, by the Borde detector or by Na64 at CERN. Let me show you Na64. So this is essentially a giant X-ray tube. Electrons come in at 100 GeV. They hit a target, and inside the target, there may be processes, and parts of the electron energy may be converted into dark photons. And now you can do two things. Either you can hope to detect the dark photons by waiting for them to turn back into regular photons and detect them. These are the so-called visible mode limits, and they give rise to limits as plotted down here. Or you measure the energy deficit. So you assume that the dark photon is lost and the energy is never recovered, which means the electrons here will have an energy spread depending on how much energy has been converted to dark photons. That gives rise to these limits here. I should say that all these limits, the visible and invisible limits, make some assumptions on branching ratios in those reactions and are not completely comparable and not completely general. Okay, now finally to the topic of my talk, alpha from H/m. How do I do that? The equation here on the slide is in disguise the energy of hydrogen in the Rydberg energy, essentially. So the energy in the lowest Bohr orbital in an atomic physics class, you would say, is H times C times the Rydberg constant. In a high energy physics class, you would say it's 1/2 alpha square MEC square. In other words, the fine structure constant squared divided by 2 is the ratio between the electron rest mass and the energy of a hydrogen atom, right? I can solve this equation for alpha if I know the ratio of the electron mass to the Planck constant and the Rydberg constant. The Rydberg constant is known from the hydrogen spectroscopy experiments by Thomas Udem, Ted Henge, and other people. It's in fact the most accurately known fundamental constant, so no problem here. H/m is more of a problem. It essentially implies measuring the electron mass in kilograms to extremely high accuracy, which nobody can do. Fortunately, the ratio of the electron mass to the cesium mass is very well known. Okay, and so I can replace the measurement of H/m electron by a measurement of H/m cesium, and then I combine all three to get alpha. So let's see, and the least accurate link in the chain is the measurement of H/m, so that's what I'm going to focus on. How do I do that? Well, in principle, it's easy. I have an atom in a state A here, and I hit it with a photon with a momentum h bar k, and then I measure the velocity at which the atom recoils. That velocity would be h bar k over m. Knowing k and knowing the velocity, I can solve for h over m. The problem is, how do I measure this small velocity of 3.5 millimeters per second? The only tool I have is the Doppler shift, and that's 2 kilohertz out of 350 terahertz. So I need an accuracy of 10 to the minus 10 to even show that the effect is non-zero. And in order to get a competitive measurement of alpha, I would need to pinpoint this 2 kilohertz Doppler shift to the microhertz level. That would be a 22-digit measurement. And that is, quite frankly, infeasible. And again, why is this so hard? Because I'm subtracting two large numbers, the atomic transition frequency and the Doppler shifted transition frequency, in order to get a small number. That's inefficient. So how can we avoid having to do that? And the answer is building an atom interferometer. At this point, I want to show some of the people that were involved on the first day, because this was actually how I started my postdoc in 2004. The upper right picture shows some of the people that were involved. Shengwei Zhao is now at JPL working on atom interferometry. And the picture on the lower right is Steve Chu was Secretary of Energy at the time, and he was most insistent that we wear goggles all the time because the last thing that he needed was an accident in the lab. Here's some other pictures of the Chu group. Cool. So how do I do that? Here's an atom interferometer in which the red line is the trajectory of an atom freely falling under gravity. At a time t naught, here, I kick the atom with the momentum h bar k of a photon or of a pair of photons. It moves up. With more photon kicks, I invert the motion and they interfere at the end. The phase difference between these two paths contains a term from the kinetic energy when the atom moves here. That's given by the recoil frequency h bar k squared over 2m. The number little n squared here is the number of photons that I use to kick the atom with. If I use 10 photons, I have 100 times the kinetic energy of using 1 photon. So that's a lever to increase the signal here. Unfortunately, all this happens under gravity, and gravity causes a way larger phase shift between the interferometer arms. You can hand wave that by noting that the typical free fall velocity after 1 second of experiment is meters per second, whether the recoil velocity we're talking about is only millimeters per second. So the unwanted signal is much larger than the wanted signal. What do I do about that? Well, I can try to cancel the unwanted signal, or I can try to make the wanted signal larger. And in the experiment, we're doing both of these things. Let me hold on here and wait for your questions for a little bit.
Okay, so we have a question from fellow panelist Alicia Kolar. So she wants to know, are atom number fluctuations and collisional shifts due to high densities part of the reason you chose not to use a BEC, or is it more related to the rep rate and amount of time it takes to produce a BEC?
Well, the honest answer is it's more related to the time and money needed to make a BEC. Mm-hmm. Let's put it this way. When we started building this experiment, nobody had ever done a precision interferometer with a BEC for the reasons that you mentioned, and collisional shifts, mean field interactions, and so on, right? That happened a bit later, and actually John Close from University of, I think, Australian National University, showed that if you do it the right way, you can work with BECs without suffering from these effects. But that wasn't known when we started this experiment. When we started the experiment, we also didn't know that this averaging over wavefront distortions would be important. So the reason we did not use a BEC is that we thought we would not need it, and we could save a lot of time and money by not building one, right? It's actually funny that a competing team in Paris, or I should say collaborating team, because the fine structure constant is important enough that you can do 2 measurements without having a crowd, right? they actually did build a BSC machine, but they are no longer using it because they have more systematics when they use a BSC. Does that answer the question?
Looks like Alicia's nodding. Iris Kong asks, is there a particular advantage to using cesium? Is there a different atom you'd like to use next? And I'll kind of combine that with, would it be actually helpful? Is there a benefit to maybe perform this measurement with multiple elements if you could build multiple experiments?
Okay, let me try to address all three questions. So cesium isn't a bad choice. It's also, but I would say at this stage, the choice of atom doesn't make a huge difference. Cesium is good because it's heavy. Why does that? You would say that's unintuitive because the recoil frequency goes like 1/m. So you might ask, why don't you use a lighter atom to have a larger recoil frequency? And the best answer I can give in 1 minute is our signal comes from kinetic energy, whereas most of the systematics come from motion. So I want to have a lot of kinetic energy with not so much motion. And so I want a heavy atom, okay? That makes cesium slightly better than, let's say, rubidium, but not by much. On the other hand, rubidium has a smaller mean field shift. Cesium has a larger one, but we're not limited by that yet. You could go to a fancy species such as strontium or terbium, make use of the fermionic isotope to completely eliminate mean field shifts, but we're not limited by them right now. Now, the third question is actually very interesting. And I would say, if one would ever find a big discrepancy between alpha and G-2, then the first thing I would check is the theory, which involves 10,000 Feynman diagrams and more, right? And if that doesn't yield a solution and people start being serious about, wow, is this a signal for new physics? Then you should really try out everything in your power to confirm it. And then I would say, let's do it with 2 species in the same apparatus. So you can clearly separate some systematic effects that would still be common and some that would be different. I think that would be our best, actually the next step once somebody would find a big discrepancy with G-2. Does that answer it?
Absolutely, yeah, I think so. Okay, so why don't we move on and we'll save the rest of the questions for the end of your talk.
Okay, I might give you another chance to ask questions. We'll see. So we said try to increase the signal and try to cancel the unwanted signal. So how to do that? For increasing the signal, we use multi-photon Bragg diffraction, right? So we're shining in 2 laser frequencies. The atom starts in the non-moving ground state here, absorbs 1 photon, goes to a virtual level, is stimulated to emit a photon at another frequency, but at this stage, energy momentum conservation is not satisfied. And the laser frequencies are tuned such that, in this case, after interaction with 1, 2, 3, 4, 5, 6, 7, 8 photons, the label here is wrong, energy momentum conservation is satisfied. And that's how we can kick the atom with the momentum of, let's say, 8 photons, but not with 6 photons and not with 10 photons. In reality, we use 10 photons most of the time. If we want to use way more photons, the needed laser power goes up because each time you get a little suppression factor by those little detunings here, right? Okay, to cancel gravity, we run 2 interferometers. They are more or less upside down copies of one another. So the recoil signal and the gravity signal have opposite signs between the 2 interferometers, and I can double the desired signal and cancel the gravity signal. This cancellation is almost perfect, except that the upper interferometer flies slightly higher, and so it's a little bit further away from the center of the Earth. So the cancellation is not perfect, and we'll talk about that soon. It's actually interesting how we extract the signal. If I use multi-photon beam splitters, my interferometer gets so sensitive that I can't see the interference fringes anymore. They get washed out by vibrations. But vibrations cause 1 phase shift in the upper interferometer and the same phase shift in the lower interferometer. So by taking the outputs of the two interferometers and plotting them parametrically, I get an ellipse. The shape of the ellipse is determined by the signal that I want to measure. And in each experiment, which point on the ellipse I get is determined by vibrations. So all I have to do is let it plot an ellipse for a few minutes, fit the shape of an ellipse. And in theory, I'm getting one measurement of the fine structure constant. The plot here shows the actual signals. The atoms, after the interferometers, there are 4 groups of atoms exiting the interferometer. The first interferometer gives rise to these 2 peaks on the right-hand side. The other interferometer gives the 2 peaks on the left-hand side. And the stuff in the middle is atoms that for some reason have not taken part in the interferometer. We can insert Bloch oscillations here in the middle to pull the interferometers apart further and get even more signals. That's shown here. If I have 50 Bloch oscillations, the interferometers are further apart and I get a larger signal at some loss of atom population. These plots are all to scale, right? The reason after scanning, let's say at 5 milliseconds, we now measure at 10 millisecond pulse separation time. So increasing this pulse separation time, letting the atoms accumulate phase for a longer time, gives us more signal. And by measuring at a series of pulse separation times, I get a tool to diagnose systematic effects, because the desired signal is strictly linear in T. So if I find something that doesn't go linear in T, I have discovered a systematic effect. And we've performed this experiment for months and months and actually years until we had a model of every single systematic variation of the data ever noticed. Here are those Bloch oscillations. So in the middle between the second and the third beam splitter, I insert a Bloch oscillation section, and unfortunately Zoom is covering the equation. The key number here is, it's getting even worse. Inside that parenthesis, there's a little n plus big N, and big N is the number of Bloch oscillations, which can be hundreds. The momentum separation between the fastest and the slowest atoms at the outputs here is up to 800 photon momenta h bar k. Okay, here's the setup. Atoms are trapped in a fairly conventional magneto-optical trap, followed by moving molasses launch. So an optical molasses is moving upwards, launching the atoms into free fall. There's Raman sideband cooling up here to reduce the temperature a little more, and the interesting stuff happens inside this magnetic shield. It's 1.6 meters tall, so in theory we could operate for almost 1 second with those atoms, but in practice we only go to a pulse separation time of 18 milliseconds. Why? The signal goes like T, the gravity gradient systematic goes like T cubed. So we want to work at the shortest T that still gives us enough signal. That's why. Okay, here's a picture of the interferometer. Everything looks fancy if photographed with a fisheye light lens, right? Do those interferometers always have to be that large? And so here's a short excursion, and that's giving the answer, no, they don't have to always be that large. Let's assume we put all this into a cavity, and let's assume we use the cavity mode as an optical dipole trap to hold on to the split wave packets. This is Vicky. She looks happy because the experiment works. Cavity is in here. And then I can beam split the atom, put it in the optical lattice in a superposition of being at a higher lattice side and a lower lattice side, and hold it for 200 milliseconds, 1 second, 5 seconds, and up to 20 seconds, and I still get interferences. If I wanted to do that in an atomic fountain, I would have to build it 500 meters tall. Granted, this interferometer right now does not have the high accuracy that we want in a fine structure constant measurement, but I would say it's for sure the longest lasting spatial superposition of wave packets ever demonstrated. And I think that's important because in any quantum technology, I need to make sure that the signal accumulates faster than decoherence destroys my quantumness, right? And here we have kept the quantum superposition alive for 20 seconds. That has good implications for making this thing less sensitive to vibrations, but let me skip over that. Okay, here are those famous ellipses. Again, a measurement starts with scanning from 5 milliseconds to 80 milliseconds. We fit a model that involves the wanted signal, gravity gradients, and known systematics to the data. And that gives us one measurement of the fine structure constant in every 20 minutes or so. Doing that for a day produces one data point that goes into the master statistics later. And then doing that for about 30 days, but not consecutive days, taken over 3 months or so, gives the final result. I should say that if we were not interested in accuracy, but just in precision, you know, precision is the ability to sense a small change. Accuracy is the ability to actually tell you what the number is. So if being very sensitive was our only goal, we could reach 0.2 parts per billion in 1 day, but we had to measure 30 times as long to eliminate systematic effects. Even after we're satisfied that we've done a good job, we still run the experiment again and again, varying, for example, the number of Bloch oscillations, the laser power. We vary the contrast by making it worse on purpose and see whether this changes alpha or not. We detect only the left-hand side or the right-hand side of the atom cloud, and so on and so on. Crank the bias B field up tenfold and see if something happens. And again, we ran the experiment so long until we understood the influence of all these things. And one thing gave me confidence. One day we noticed the fine structure constant was different, very different. And we were very puzzled until a few days later, the grad student found that a laser beam was misaligned. So we fit the amount of misalignment, we put the amount of misalignment into our Monte Carlo model of the fountain and saw that the computer predicted exactly the amount of change in the fine structure constant that we had observed. So these things give you confidence that indeed you have accuracy and not just precision. And then we get results, and here is the result. The big arrow bars are again quantum Hall effect, fine structure, and so on. The two most accurate previous measurements and our result are zoomed in here on the right-hand side. The green arrow bar here on top was an H/m measurement with rubidium atoms conducted at Laboratoire Castres-la-Boisselle in Paris in 2011. And you see that our measurement is compatible with it within the error bar. The error bars completely overlap. The red one is Jerry Gabriel's measurement of the fine structure constant through G-2. It has 0.24 parts per billion accuracy. We have 0.2, and there is a discrepancy by 2.5 sigma. In modern particle physics parlance, this is called a tension, because discrepancy would imply 5 sigma or more, right? So there's a tension between them. But before we talk about the tension, let us behold the fact that two completely different types of measurement connected by probably the most involved calculation in physics agree to 10 decimal places. Okay, that's an enormous success for the fine structure constant, or expressed in in gyromagnetic anomaly, right? How much is the gyromagnetic moment different? It's even a 13 decimal places agreement. We would have thought the standard model breaks down way before that. So I think the zero order message here is it works out, physics is great. But now, of course, we're scientists, we want to know what's going on. So let me put it in context. Here again, the contributions from the standard model to G-2, right? here are the two measurements by Gabriels and us, and you can see that at the current accuracy, we see the fifth order quantum electrodynamics contribution. We see the contribution of the muon at about 10% accuracy, or 10 sigma. So this is a low energy measurement in the lab where I get a 10 sigma signal from the existence of muons. We're about an order of magnitude away from seeing the tauon or the weak interaction. We see the hadronic influence also at about 10 sigma. So this again is something that's going on an optical table, and that's sensitive to the existence of hadrons. We are also proposing to make this about 10 times better. The same is with G-2, and I'll talk more about that at the end of this talk. Okay, let's put it in context. So what might be going on with these 2.5 sigma? And all of that is way above my particle physics pay grade. So I let the literature talk about that. The plot on the left is taken from a particle physics blog. It plots the known G-2 anomaly for the muon on the y-axis and the one that we measured for the electron on the x-axis, and put some rings around there for 1 sigma, 2 sigma, 4 sigma deviation from the standard model. And the deviation from the standard model of the combined lepton magnetic moments is more than 4 sigma. So if you're a member of the Holy Church of 5 sigma, then you should get worried at this point. And then after we published our result, lots of particle physics papers came out from good people, and this is one by Marciano and w.rt. They claim that the two discrepancies, if they are real, could have the same reason. There have also been papers that say the fact that the two discrepancies have the opposite sign is proof that they cannot have the same reason. I'm not taking a position here, I'm just reporting the two positions, right? What does it mean for the existence of dark photons? So if we take our data and see which dark photon coupling strength is compatible with our data, then it actually improves upon the Na64 result by a little bit. And this was fortunately the situation when we published our paper. By now, Na64 has overtaken us by a tiny bit, but we'll catch them soon. This is again the dark photon limits. Let's not worry. Yeah, and this is again the w.rt paper where they say they can have the same reason, the discrepancies. Here's an opposing point of view where they say they cannot have the same reason. Systematic errors. Most of them come from the fact that a real laser beam isn't a plane wave, and that means the momentum, the local wave vector, and therefore the momentum of photons is different everywhere. That causes an error even on the beam axis, known as the Goye phase. That's 3.6 parts per billion here. Let me point out the Goye phase shifts alpha by 3.6 parts per billion, but we can measure it with an accuracy higher than that. Okay. This also means that we need to apply corrections to the data depending on where inside this beam the atoms are. Okay, so we need a model of how the atoms move through the laser beam, and that gives rise to this relatively large error that's denoted thermal motion of atoms here, 0.08 part per billion. You might think that 0 plus minus 0.08 is a bit pathological. Why is it exactly 0? The reason is that the 0.08 part per billion error bar is how much we trust our Monte Carlo simulation. The Monte Carlo simulation itself predicts an error much smaller than that, but we have given it a larger error bar here based on its ability to analyze fake data. So you put fake data in the data analysis code, and you see how well you can extract the fine structure constant from it, right? So this error could be shrunk by better modeling of the experiment. Anyway, what I want to show is I want to group the systematic errors in two classes, the big ones here and the new ones. And the good news is that the big ones aren't new and the new ones aren't big, right? So people have measured alpha by similar ways for a long time, and pretty much the error budget is well understood. The other thing I want to point out is almost all these contributions to the error bar are in some way related to the quality and thickness of the laser beam. You could imagine if the laser beam was a perfect infinite plane wave, then all of a sudden it doesn't matter where the atoms are. And so this thermal motion of atoms error goes down, right? And that's essentially our path to improving the measurement 10 times. What we want to do is use a larger and cleaner laser beam, and that addresses a large number of these systematics at once. We want to also do better characterization of systematic errors. Notably, the acceleration gradient here comes from the fact that gravity for the upper and lower interferometer is slightly different. And you could either measure the gravity gradient better, or you could build an interferometer with 4 measurements at the same time to cancel not just gravity, but also the gravity gradient. And with that together, we want to get an order of magnitude improvement. So let me show you how that is supposed to work. This is all making use of the great labs in New Campbell Hall, where there is a little pit inside an acoustically shielded room to keep the vibrations out. It's an atomic fountain like we've run it before, but the biggest difference is, look how thick this will be. This will be about 1 foot thick, giving us a clear aperture for the laser beam of 8 or 10 inches inside the magnetic shield, when right now we have much smaller. And what that means is we can now use a much thicker laser beam and yet have less scattering at the vacuum chamber walls and therefore less speckle. Okay. So here's some pictures of the next generation, how we want to build it, right? Vacuum system. This is the magnetic shield that we had to return because of a manufacturing error. The new one is being made. We will collaborate with scientists and engineers at LBL, which is great. There's experts for high power fibers. You can imagine that having a very thick laser beam requires a lot of power. And how do you get that power through a fiber? High quality CCD imaging for atom detection and also for characterizing the beam, and mechanical engineering for keeping all this vibration free and stable, right? Here again, the idea with the thick laser beam. So we could reduce wavefront errors by a large factor. How do we get so much laser power, by the way? I want to show you a little bit how we did that. So the idea is to start with a seed of hundreds of milliwatts at 1064 nanometer, amplify it to the kilowatt level in pulses. So we'll generate light only when we need it, which means we can increase the peak power 100 or even 1,000-fold without increasing the average power that much. Then we frequency double it to 532 nanometers and use it as a pump for an optical parametric amplifier to amplify our existing laser beam. This idea is due to Dave DeMille at Yale and has been tested by him, except for the OPA. That hasn't been tested yet, but so far, so good. Let me show you some data actually measured by Andrew Neely in our lab. So we start with 300 milliwatt, and after 2 stages of power gain, we achieved several kilowatt of power. We have damaged lots of mirrors with those pulses. Here's a measurement of the frequency doubler, which has nearly 60% doubling efficiency, which is all we need, right? Here's the interferometer geometry that we want to run for eliminating the gravity gradient. This work has been accepted by peer A recently. So essentially by taking the interferometer C and the interferometer B we can have a gravity gradient-free measurement of the fine structure constant. But by using other combinations of the 4 interferometers, we can measure systematic effects at the same time as we're measuring alpha. So this should also speed up the data collection. There are some new ideas of how to do beam splitters that I won't have time to mention, unfortunately. And with that, I want to close. Let me just show you the new physics reach of the measurement. So here is another dark photon exclusion plot. The shaded areas are existing dark photon limits, and the lines in here are projected dark photon limits from experiments that haven't been performed yet. And I don't know, I'm not a particle physicist, I don't know which of them are very likely to happen. Some may already have started, some may already have been canceled. But what we want to do is set a limit at this red line, and depending on which experiments have come online by that time, it might be the best limits on dark photons in some region of the parameter space, but it's certainly in good particle physics company. So conclusion, measured alpha at the 0.2 part per billion level, trying together with LBL to improve it a lot. And with that, let me show you a picture of my group. Let me point out especially the people that were on the old experiment. That was Richard Parker, Cheng Wei Yu, Wei Cheng Zhang, Joyce Kwan, and myself. On the new experiment, we have Wei Cheng and Zachary. Madeline works there. She's not on the, sorry, this is an old slide. So Madeline Bernstein is not yet on there. There are scientists and engineers from LBL listed here, visiting students, undergrads. Thank you very much for your attention.
Okay, thanks, Holger, for a great talk. So we have a few more questions for you. So Guanchen Peng asked, when you mentioned the gravity signal in the interferometric phase, is it from the laser phase or free evolution phase, or actually both?
Both. It would be entirely from the laser phase in a so-called Mach-Zehnder interferometer, which is more symmetric. But in this less symmetric Ramsey Borde, the two contributions are about the same size, roughly.
And then Jonathan Kunjaman asks, could this experiment, and in particular the acceleration gradient noise, benefit from being conducted in space so that the entire setup is in free fall?
In theory, yes, but to make it happen in space is a tough task. So NASA has a cold atom lab on the space station. It's not set up to do, let's say, extremely high precision measurements, but it has run an atom interferometer as of this week, as far as I know. Maybe it was last week, but at least this week is when I heard about it. So in principle, the technology is now there to perform atom interferometry in space, which is a big step, right? The problem I see right now is mostly a cultural one. In atomic physics, we are not used to running experiments remotely, like they can do in other fields of physics and particle physics. Or in astronomy, nobody goes to the observatory at night and looks through the telescope with their eyes, right? It's all remote controlled. But in atomic physics, we like to go to the lab, misalign a mirror mount and see what happens. And so doing this measurement completely remote controlled, I think, is a big challenge that right now I don't know how to do.
Okay, Luis Lopez asked, do you use seismometers to actively suppress or account for vibrations?
I'm sorry, you're...
Oh.
So you were cutting off for a bit, but I think I know. Could I use a seismometer to cancel vibrations? The answer is I don't have to, because they cancel anyway in this differential measurement. What I would gain if I had a seismometer, and that would work perfectly, you could imagine when I take ellipses, 50% of my data points sit in corners where they don't really contribute to the phase measurement. So the price I pay with ellipse fitting is I need twice as much data to get the same statistical accuracy. So with a seismometer, I could in principle eliminate this factor of 2 in averaging rate. But there is no pressing need, let's say, in terms of accuracy to do this active cancellation. This is being done in other experiments. For example, atom-interferometers for measuring gravity often use cancellation schemes like that.
Okay, we have a couple sort of related questions from a couple of the other panelists, from Alicia Kohler and Monica Schleier-Smith. So they both were wondering about what the whether there's an advantage or what the advantage of using a cavity for holding atoms rather than just an optical lattice in the the data that you showed on holding. And also, are you planning on doing holding in the next generation apparatus? And is there an advantage to using a cavity to clean up the wavefronts actually?
Yeah, so wavefront quality is the answer to why is it better to hold in a cavity. Holding atoms in optical lattices without cavity has been tried and was limited to 1 second. Our experiment was in a cavity, achieved 20 seconds, and I'm pretty sure that that progress is because of the cavity. Is the cavity-based interferometer the ideal system for measuring alpha? Right now, I would say it's not, because you see that our next generation alpha measurement doesn't use a cavity. So, and the reason is this. In a gravity measurement with a cavity, I can keep the atoms at rest in the lattice, right? But the alpha measurement is based on motion of the atoms. Now with Zach Pagel's ideas to make optical lattice beam splitters, I could do that in principle. But we would need to run the entire analysis of systematic effects again. Whereas we think that with engineering improvements, we can improve the accuracy of our old methods by a factor of 10 without reinventing the wheel, so to speak. So that's why we're not yet doing that. Would it help to use cavities to clean the wavefronts like LIGO does, right? In principle, the answer is yes, but there's a but. We have one symmetry that we use in the experiment all the time, namely the ability to change laser frequencies a little bit without changing the laser intensity. That's an important tool to characterize systematics and change between one interferometer geometry and a different one. If I use cavities as wavefront filters, then I lose that advantage. That doesn't mean I cannot use a cavity, it just means it's complicated. And we will use that, let's say, if it turns out we absolutely have to. But right now, we hope we can get away without.
Okay, so I think maybe we'll take one more question and then we'll pass it over to John to round things out. And then maybe afterwards we can have some more discussions sort of offline unofficially as we've done in the past. So Heinrich Becker asks, what is so difficult about simulating the thermal motion of the atoms? It seems like this is a major source of systematic error. So is there any way you can reduce that error by a large factor?
Yeah, we definitely could. Why did we not do that? Because our accuracy right now is 0.20 parts per billion. I think if we would have reduced the modeling error to exactly 0, it would have become something like 0.18 part per billion or so. So there wasn't much incentive to improve it. Our modeling effort was focused on getting it bug-free. We set out to program the entire data analysis was programmed by 3 different people independently to make sure that we have a good chance for spotting bugs, right? And doing all that again would have taken us a lot of time. But in principle, there's no fundamental problem with getting that error bar down further.
Okay, well, thank you, Holger, for a beautiful talk, and thanks to all in the audience for coming. Please join us at noon Pacific, 3 p.m. Eastern time next Friday for a talk by Vedika Kameni from Stanford. Also note that our European sister series, the Quantum Science Seminar, will be featuring a talk by Klaus Malmer, and that's at 11 a.m. Eastern time next Friday. So thanks again, everybody.
Thank you.